why we are doing image processing. Now we will learn how to do image processing. So in this session, we will learn about some digital image processing techniques plus some edge detection techniques. These are fundamental steps in computer vision and AI-based image analysis tasks. So also by the end of this session, you will understand how images are represented numerically, how to perform some essential image processing techniques like resizing, grayscale conversion, and noise reduction. Also, how to use standard edge detection techniques, traditional techniques like Sobel, Privet, Laplacian, Kenny, as we discussed in Prinkamem discussed in image processing lecture. So we use these four libraries for image processing. So OpenCV is core image processing toolkit. It contains lots of basic image processing functions. NumPy is for numerical operations in image arrays, and matplotlib is to visualize the image. And Google.colab, we will use this for upload the image in Colab. So we import NumPy as NP, and we import CV2 which is OpenCV, and we import PLT from matplotlib.pyplot. Also we import files from Google Colab. So okay, this is the code for uploading a file from your local system to this Colab notebook. So you have to use files.upload. So it will gives us a option to choose a file from our local system. So okay, I'm running this code because it will take a while to upload the image. So there is option for choose a file. So okay, I want to upload this image. This is image from HRF data set, which is data set of retinal fundus images. It is containing normal diabetic retinopathy and glaucoma eye. So you will see next step that it is a large image. That's why it takes this much time to upload. And okay, then first we upload the image, then we get the file name. What is the file name of this image? So after getting file name, we read this image by CV2 IM read. So CV2 read image in BGR manner means blue, green, and red channel. But in journal, we use RGB images, which is red, green, and blue. So we convert this image to RGB. We use function CV2 dot CVT color, and we show this image. How to show the image? As Rinki ma'am discussed this many times in previous hands-on. So you have to first give the size of figure, then plot.image show, and title for the image by plot.title. And if you want to access, you can on this, or you can off this if you don't want, and then plot show. So this is the image. Now, first steps comes in mind that what is its size, or you can say it resolution. So we say we name this image RGB. So size of to find size of image RGB, just use image RGB dot shape and print this size. So image size is 3504 cross 2336 pixels, and it has three channel, which is red, blue, and green, which we'll discuss further these channels. So this is a large image. So we want to resize this because if we have lots of images of these sizes, so it will take lots of time to process them. So there is something called image resizing. Why resizing? Because it help us to make a standard image data. So different images have different resolution, different size. So if you want to compare them, or we want to use as input in to train a neural network or any other task, we need a standard size. So we use this resizing. Okay. So just like 224 cross 224 is commonly used in deep learning models like VGG, ResNet, and 512 cross 512 resolution is used for medical or high resolution image processing. And 1024 cross 1024 is considered close to original resolution. It is used for detailed analysis. So how to resize the image? There is a function for this in CV2 library, a CV2.resize. It will take two arguments. One is your original image and then size of the image. Okay. So after you will get resized the 224, 512 and 1024. So like this, you can resize this image. So okay, you know how to plot this. So I will not discuss this as Rinki ma'am discussed in previous hands-on sessions. So look at the size of the image. Okay, you want to just say you want to resize it to okay 2000 cross 1000. Okay, you can do that. So you can write here name for this 2000 cross 1000 and run this code. You will get this is last image is 2000 cross 1000. Okay. So okay. And next is if you want to check it is resized or not, you can check this size of this image. So I checked resized 512 dot save. So this is 512 cross 512 pixel. It has three channels. Okay, and now on we will use this resized 512 because we want to save computational time, and also it is a good resolution. It preserve visual detection, which is important for edge detection and image analysis. So we will use image RGB as resized 512. Okay, next is how a computer sees an image. As we discussed, computer sees as image as pixel intensity value. For every pixel position, it has three intensity value: one for red channel, one for green channel, one for blue channel. What is red channel? A red channel, it shows intensity of red color. Second, green channel stores green intensity and blue channel stores blue intensity. So basically, there is something called vector space in mathematics. So for a vector space, there is a basis and there is a dimension. So dimension is cardinality of basis set. So using basis, we can generate this vector space. If you have like a vector space of all the colors, so you can generate these all the colors by red, green, and blue. So basis is red, green, and blue, and dimension is three. You can do this by other combination, different combination of three colors, but RGB is generally used. So okay, if we print whole image as matrices of pixel intensity, it will be 512 cross 512, and we will get three matrices for red, blue, and green channel. So first we crop the image. Okay, we want to take 15 cross 50 image. So first we crop. How to crop? Nothing. Just insert this close bracket and put the desirable range in which you want to crop the image. And how to find red, green, and blue channel? So RGB image array starts from 0, 1, 2. 0 is for R, 1 is for green, 2 is for blue. Okay, you got this. We print these details. Okay. So this is the original image. This is the corresponding cropped image. Now sees this pixel value of this cropped image. So this is 15 cross 50 pixel region, and we get this. You can see this image is reddish image. That's why intensity is larger than these green and blue intensity. So that's the role of channels, because as you can see, this is some close to reddish color. So that's why a red channel is has more intensity, and this intensity value is between 0 to 255, because these computer use 8-bit system. So these pixel value will be between 0 to 255 pixels. Okay, now we want to extract red, green, and blue channel from the image. Also, we want to convert in grayscale image. Grayscale image, why grayscale? Grayscale image is also a single color image. It contains only the brightness information. It does not contain any color. In some task we need only brightness information, where we just like pattern recognition, where some tasks don't need color, like medical imaging need colors. For that we use RGB images, but some task does not requires color information. To reduce computational time, we use grayscale channel. How to get these channels? So for red channel, we find this using 0, green for 1, blue channel from 2, and we first we define a red channel image by np dot zeros, like because first we want to make an image of size image RGB. That's why we use this command, and we print these images. Okay, so you can say red channel is a reddish channel. Green channel have different type of information. Red channel has different type of information. Blue channel has different information. Gray scale different information. So just like think of that. So if you want to detect the blood vessel of this retinal fundus image, so which channel you will use? You can use grayscale channel, or you can use green channel. So as you can see, green channel vessels are clearly visible. What is use of red channel? Okay, you want to find the region of interest. There is a black region from all the sides of this retinal fundus. So we don't want to process this unnecessary region. So you want to find only a region of interest. For that, this red channel is very useful because it shows clear difference between foreground and background. And grayscale channel and green channel can be used for further process the image. Okay, how to find inverse of an image? So maximum pixel intensity 255. So just apply simple and subtract this image RGB from 255, so you get this inverse image. Okay, so you discussed some point processing techniques in Prinka ma'am's lecture. Till now, any doubt? Please paste in the chat bot. Do you have any doubt? You got these basic things. For this hands-on session, you don't need any barrier, any prerequisite or any knowledge. You just have to follow these instruction, and you will learn. So for point processing techniques, what is point processing techniques? It it applies on a single pixel, and we apply a function on each pixel, same function on each pixel, and we get different image. So first is brightness and contrast adjustment. So for that we apply a into f plus b, this transformation to every pixel value. So A controls the contrast. If A is less than 1, it reduces contrast. And if A is greater than 1, it increases contrast. What is B is doing? B control brightness. B is less than 0, it darkens the image. And B is greater than 0, it brightens the image. Okay. So A is 1.5 means A is greater than 0, so it will increase the contrast. And B is greater than 0, it brightens the image. So it is, as you can see, it is brighten the image. Okay. There is a function for this CV2 dot convert scale ABS. So you have to put three argument: image RGB, a value of A, and value of B. Okay. But this is the simple transformation, so you can create by just simple mathematical operation. So just simply multiply the image by A and add B to it. So you will get the, and we convert this unit 8, np dot unit 8 for visualize the image. Okay. So this is the same image. Okay. So if you want to, okay, let's see, A is less than 1, then it reduces contrast. Let's see. So it reduces contrast. If B is negative, then it darkens the image. Okay, check. So it darkens the image. This just like this, you can apply different image transformation. Okay, do this. So this brightens the image and increase contrast. Just like that, you can use different A and B. Next one is thresholding. What is thresholding? If you want to specific pixel intensity to be picked and some specific pixel intensity to be dropped, you use this method. Or you want to find a region of interest for the image processing, we can use this technique. So what it does, so let's say you have a threshold T. So if pixel intensity is less than T, it will replace it by 0. And if pixel intensity is greater than T, it will replace it by 1. You can replace it by 1 or 255. 55. Okay, so there is a function for this CV2 dot threshold. It is useful for grayscale image. Okay, you can use it for RGB images, but you have to apply on all three channels differently and then merge them to make a color image again. So it gives us two output. One we are not using, and another binary, which is the binary image converted by this threshold function. And one we are not using output is we can use different thresholding method like Otsu's thresholding, ISO data thresholding. There is a specific function for this. So these method also gives us desirable threshold value also. So by using this, okay, I am using pixel intensity at 20. Okay, what if I use 100? Let's see. So it convert according to 100. What shows 20 shows only the our fundus area. So if you want to process the fundus area only, then you can find this region, and by multiplying this region, you will get only fundus area. Just like the previous, you can manually make this thresholding function also. How? Okay, T0, just like that. First, I generate a binary image. All the entries are 0 and size is image RGB. So all the entries are 0. If T is greater than equal to image intensity greater than equal to T, I want to insert 1. Okay. I insert the 1 and other is already 0. So we get this image. Okay. T is 120. And we are using it for gray scale image. Okay. Sorry, there is some error. Okay, error occurs due to this. We have to use gray image. So this is grayscale because uh, here image RGB means we are generating a 3-channel image. All entries are 0, but we are using gray here. So that's why error comes up. So you can use manually. You can use thresholding manually. If you want to insert 10, okay, you want to insert 10, okay, you will get this image. If you want to insert any value, you can insert any value and you will get different values. Okay, next one is gamma correction. It is a non-linear enhancement technique. It is also a point processing techniques. So in gamma correction, we power of every pixel by power of gamma. If gamma is less than 1, it brightens the image. If gamma is greater than 1, it darkens the image. How to find gamma function? Nothing. NP dot power. image RGB divided by 255 because we want to normalize the image. Okay. If we take image no original image pixel, it means some is the image pixel is 181 as you see in our matrix. If 181 and we power it to 2, then it will cross the 255. So we want to normalize this. That's why we divided by 255 and gamma value is 0.5. And then first we reduce the size, then we multiply by 255 to power up the size. Then we use this np dot united to convert in visualize home. Okay. 4.5 means brightens the image. Okay, we get this. Okay. What if I put 2 here? It means it will darken the image. Let's see. So it darkens the image. You can insert 3. So it darkens the image. Next is histogram equalization. Histogram equalization is used for grayscale image. Okay. So every image has pixel intensity as every pixel position. So let's say we have 0, 1, we can have 2, we can have 255, up to 255. Total number of pixel level, intensity level is 256 because 0 to 255. So L is 255, 256. Okay. So first we choose a pixel intensity level. Let's say we choose 10. Then HRK, number of pixel with intensity 10. It means how many pixels are there with intensity value 10, which is H. Then we find P. P is nothing but total number of pixels means size of the image, and we divide number of particular pixels of particular intense number of total pixel of particular intensity by total size. So it normalized it. Then how to perform this equalization? Then for each pixel value we insert for each pixel value we assign a new pixel value which is generated like this L minus 1, which is 255 because L is 256, and sum of all these PRRJs. Okay, so these are the output image. As you can see, for this we have this CV2 dot equalize hist function. So this function highlight the blood vessel more clearly. So if we apply this as pre-processing tasks, we have more chance to detect good edges, because in original images and in histogram equalized image you can see clear difference between blood vessels. Next is color correction. If you have any doubt, please put it in chat board. So what is color correction? So image has three color combination of three color RGB. So you want to highlight a particular color and you want to reduce intensity of a particular color. For that we use this image color correction. So first we assign alpha. Alpha is a array 1.2 0.8. 1.2 means we are highlighting red channel. 1 for green, it means we are not changing green channel, and that 0.8 for blue, so we are reducing intensity of blue channel. Similarly, we use bias. So for red channel, we use plus 10, means we used to increase red channel. For green channel, we don't want any changes. And for blue channel, we want to reduce this. Okay. So as you can see, this is original image, this is color image. Okay. For this, we have to apply this for loop. So from range of 3 means for all three channels. So similar, same code, convert scale ABS, which we use for contrast enhancement, and we get these images. As you can see, color corrected image is a reddish image. Okay, you want to make it more reddish. Let's see. Okay, it is more reddish. You want to make it more reddish. It is more reddish. So just like this, you can make the color correction in any image. So next is spatial image processing techniques. So for spatial image processing techniques, we need a pixel and their surrounding pixels information. Also, we need that surrounding area. And based on this surrounding area, we process this pixel and assign a new pixel value in processed image. So first is smoothing. We want to smooth or average the image. It is used for noise reduction. Okay. So first, as Priyanka ma'am discussed in image processing lecture, one of simple smoothing kernel is 3 cross 3 kernel. All the entries are 1 by 9. So as you can see, np dot ones of size 3 cross 3 means we have 3 cross 3 size. Each entry is 1 and it is divided by 9. Hello.
Mr. Harish, Mr. Harish, do you have any doubt? Mr. Harish?
Okay. So this kernel is nothing but 3 cross 3 matrix where every value is every entry is 1 divided by 9. So okay, apply this average filter. So it will smooth the image. It will smoothens the image. Okay. So if you want to use 5 cross 5 filter for smoothing filter, sum of all the entries should be 1. So that's why this is 5 cross 5 filter and each entry is 1 divided by 25. So sum of all entries will be 1. Okay, so this is smoothen the image. Next is Gaussian blurring. Gaussian blurring is used for noise reduction also. So for that we have function cv2 dot Gaussian blur. Uh, it will take argument a image and a filter size. So we are using 5 cross 5 filter size and variance. Okay. So this is variance. Okay. I will put 1.5. I want image size of 3 comma 3. Okay. Let me assign the small image to this size because original image is large image and it will take lot of time. Okay. Okay. So we are using Gaussian blur here. So it smoothen the image. Okay. You can use different variants for this Gaussian blur according to your need, and this will reduce the noise. Now, I want to discuss about edge detection. What is edge detection? As we discussed in image processing lecture, edge detection help us find the intensity change in the image. And change in intensity represented by some boundary, edges, or some patterns, some objects, some features. So it will help us to extract these features, detect the object, detect the boundary, detect the edges. So there are two methods. One is for first order derivative method. Second is second order derivative method. First order derivative method uses gradient magnitude, also gradient direction. Second order derivative method detects zero crossing, just like Laplacian etc. So first one is simple edge detector, Robert's cross operator. So for this operator, we have two filters. One is in x direction, one is in y direction, which is represented by kernel X and Y. So how to apply this on the image? So CV2 dot filter 2D. 2D means we are using grayscale image, so it is a 2D image. Only it has only one channel, and 3D image means a colorful image with three channel because it has three dimensions. So what it takes is argument. It takes image -1. It means sliding window. If you want to remove first row and etc, and kernel X just like for Y direction, then we square these two edge map and then sum up and find the square root. This is the final edge. We return this edge as np.unitate edge for visualization purpose. Okay, so this is the function for robots operator we defined, and we want to find the robots edge detected by robots operator. So we apply this function. Also, I want to apply threshold here to check how it's performing here. And you know how to show these figures, so I will skip this part. So as you can see, this is the original image. This is the grayscale image. This is the robots edge map without thresholding. But in this, you are seeing edges are not sharp enough, and there are lots of noise there. So robots is with thresholding, we apply thresholding here by 6. You can apply by 8, 7 as your requirement. So it will reduce the noise and show the clearer edge map, which is blood vessels. And blood vessels are useful for analyzing fundus images and detecting various diseases like diabetic retinopathy, etc. Next one is Sobel kernel. You can use manual definition of Sobel kernel like robots. I use here manual definition 100 -1, but Sobel kernel is already defined in CV2 library. So we import Sobel kernel from CV2, cv2.sobel, and just do the similar thing as we did in previous step. We find the edge map in X direction, we find the edge map in Y direction, then we square them and sum them and then take the square root of that. Then similarly, we apply Sobel operator on image, gray image, then we apply this threshold value. Okay. So now the Sobel is detecting good edges than robots kernel. As you can see, this is sharpens the image, and this is the Sobel map without thresholding. So you barely say sees any edges here, but if we apply thresholding, you can get a clearer view of the edges, or in this case, you can say blood vessels in this fundus image. Next one is private operator. Okay, so like this, you can do for Sobel, you can manually define the kernel and then do this. So this is the private kernel, as you all see in image processing lecture. This is kernel in X direction, this is in Y direction. Then we find the edge map in X direction. Why this edge map is nothing but partial derivative of image corresponding to X direction. And image Y is nothing but partial derivative of image corresponding to Y direction. So then to find edge map, we take the magnitude of these two values, and we next steps are similar to previous steps. Okay. So this is grayscale image. As you can see, there is nothing visible in private edge map without thresholding, because edges are edges have very low intensity value. But if we apply threshold, we find this type of edge map. It is not good edge map, so we are not using this for blood vessel detection, but it can be useful for other tasks. Similarly, I just want to show how to do edge detection. You can take different images, and for different edge detector, you will get different results. If it uh, Selection of edge detector is based on which kind of edges we want to find. So for different scenarios, that's why we have lots of edge detector, because different scenario each performs differently. So next one is Laplacian operator. Laplacian operator, for this, there is a function in CV2 library, CV2.Laplacian, and we find this absolute value of Laplacian and apply it on the image. Similarly, you can see that there is no edge in thresholding. There are edges, but intensity value is very low. Very low means pixel intensity of 1, 2, just like this. That's why these are not visible, but edges are there. So after applying thresholding, we get this edge map. Okay. So 1 minute. Okay. So this is for RGB. I want to apply it for gray. Okay. Similarly, you can apply it for gray also. 1 minute. There is typing mistake. Okay. So for Laplacian image edge map is looks like this after thresholding. Okay. So reduce this threshold value by 2. So this is not working. Reduce it, increase it by 10. So okay. Now you are getting the edge map. Okay. So this is the role of thresholding. This will filter out noise. Okay. So there is a typing mistake in here also. And I want it for gray. Okay. Okay. So now Laplacian of Gaussian log operator. So as ma'am discussed, we apply Gaussian blur before the Laplacian. So we applied the same Gaussian blur, we reduce the noise, uh, will smoothen the image. Then we apply this Laplacian just like previous hmm, previous method, Laplacian method, and then we find these edges with thresholding and without thresholding. This is the similar code as previous. So you can see in here and in here lots of difference between edge the sharpness. So this is the sharp edge, because we are using Gaussian blur. So it is very helpful. So Kenny edge detector is state of art edge detector. It solves many problems we faced previously in these operator. So it has 5 steps. First step is noise reduction. It does with Gaussian blur. Second is gradient calculation. Usually we use Sobel operator for gradient calculation. So we calculate the gradient. So we get the gradient magnitude. So we get gradient in x direction, in y direction. Then we square them, sum them, and take the root. Then we get gradient magnitude. Also, we get the direction at every pixel. Direction of gradient. What is direction? At that pixel, filter image means partial derivative at y direction divided by partial derivative at x direction, and take tan inverse of this. So this is the direction. We get theta out of this. After getting theta, we did not use theta in previous methods, but we want to use this theta also, because this is information we are additionally getting in this edge detector. So we use it in non-maximum suppression. So what it does, it thins out the edges. Okay. So after computing gradient, you get direction and magnitude. Edge may appear thick. So for every pixel, we check it gradient direction. Example 0 degree, 45 degree, 90 degree, 135 degree, etc. etc. We compare its gradient magnitude to the two neighboring pixels. So we are going to one direction. So we are on a line. So we have only two neighbors. One is next one is previous one. We are in middle of two of them. So we compare them. If it is not the maximum, if R value is not the maximum, we set it to the 0. And this is how we filter out the known known edge pixels. Then we use fourth step is can use fourth step as double thresholding. What is does it classify edges in strong, weak, and non edge? It applies two thresholds. One is low threshold, one is high threshold. For each pixel, if gradient magnitude is greater than high threshold, then we say it is strong edge, and it is definitely an edge. If gradient magnitude is between low threshold and high threshold, we say it is a weak edge. It can be edge. We will check in next step. And if gradient magnitude is less than low threshold, then we say it is a known edge, and we replace it by 0. Okay, next is edge tracking by hysteresis. This is also different kind of thresholding technique. So what we are doing here? It will give us final edge map. After double thresholding, we get strong edge, weak edge, known edge. Strong edge is edge. Okay, leave them. Known edge is known edge. So replace it by 0. Now weak edge. So how to check a weak edge is edge or not edge? Okay. So first of all, we check the all 8 connected pixel. For every pixel, we have 8 neighborhood. If you have a pixel, then 8 neighborhood pixel are there. Okay. So if a weak edge is connected to a strong edge, it means their neighborhood, all 8 pixels are should be strong edge. Means they are greater than to high threshold. And if weak edge is not connected to any strong edge, then we discard this and uh, replace it by 0. So this is the Kenny edge detection code for Kenny edge detection. So first of all, we apply Gaussian blur. We are using 5 cross 5 kernel size. Or then this is the function for Kenny edge detection. So cv.kenny blood, blood means this Gaussian blood image. We are using lower threshold as 5 and high threshold as 50. You can use different threshold, and we apply this. This is cv2.kenny function or predefined in cv2 library. So we get this edge map. So as you can see, it is more visually clear than all these previous edge detectors map. So just like that, you can get for gray image. So for gray image, you have to select different threshold, because in RGB there are lots of information, but in gray we remove some information. That's why it is getting different edge map. So you have to change the threshold value, and just like that you will get some edge map. Okay, you can get this edge map. Now you can remove these small particles. You can use different threshold. Okay, so you can separate out this small noise particle from the image by using different threshold. So this is from my side. If you have any doubt, please paste in the chat bot uh, of Webex. And instead of grayscale, you can use green channel also. So okay, let's use green channel instead of grayscale. Okay, where is green channel? Here. So this is the green channel image. Apply histogram on this green channel image. Okay, there is some error. Okay, let me check. Okay, this is the green channel. Okay. Okay, so as you can, green channel have more information about vessels. So it is giving more good results in age detection also. Okay, we want to use it here in Kenny. So it will give more information. You can use only green channel also. Uh, so okay, let's use this in this Sobel kernel. So you can use this green channel also. So this is from my side. Please paste any doubt in the chat box. And I will share this